Hello everyone, my name is Madhuri Gupta, Assistant Professor, Department of Computer Science, CSVTU, Bhilai. In last lecture, we have discussed about the introductory part of Prolog, how we can download SWI Prolog, how we can do the work on Prolog and how we can run the Prolog program. Now, the today's topic is list in Prolog. In Prolog, you can create list using square bracket. As you can see, list can be empty or contain elements. Here are some of examples of list in Prolog. An example list, how we can write the list in Prolog. So, suppose your name is my list is equal to this square bracket, this is empty list. Second is a list with elements. So, your name is my list and in the square bracket you have elements apple, banana and cherry. This is the list with element. Next is a list with mixed data types. So, in Prolog how we can write it? Mixed list, that means you can have a combination of numbers and string. So, we have a list, my list is equal to 42, hello, comma 1, 2, 3 is again a list, then dog. So, this is how you can write the mix of list. And next is nested list. In Prolog how you can write the nested list? 1, 2, 3 is the one combination, then 4, then 5, 6. So, you have a nested list of elements. You can manipulate and work with list using various Prolog predicates like member, append, length and more to perform operations on the elements within the list. Now, let us define some Prolog predicates and clause to work with list. Predicate. Predicate to check if an element is a member of a list or not. So, how you can define this in a Prolog? You have to define it like member x comma x head part and the tail part is empty. Member x, then the head part is empty and tail implies that member x comma tail. So, how you can use it? So, for example, you have member 2 comma in the list 1, 2, 3. So, this will return true because 2 is the member of your list. Now, predicate to append two lists together. So, how we can append? In Prolog you have to use this append function. So, append in the empty list comma L full stop, append head tail 1 comma L2 comma head and tail 3 implies that append tail 1, L2 and tail 3. So, how you can use this? For example, append 1, 2 is a list, then again comma 3, 4 comma result. We will unify result with 1, 2, 3, 4. So, we have combination of 1, 2, 3, 4 in our append list. Now, predicate to find the length of a list. So, how you can define the length? So, you have to use the length function. So, length in the empty list initialize with 0, full stop, length empty tail comma n implies that length tail n1 comma n is n1 plus 1. Here is a function which implies the n plus n1 is equal to the next number. So, how you can use this length a, b, c, this is the one list and you have to find the length. So, we will unify the length is equal to 3 because we have 3 members in the list. These are just a few examples of predicates and clauses for working with list in Prolog. You can use these as building blocks to perform various operations on list in your Prolog programs. Now, we have some more examples of Prolog, predicates and clauses for working with list. We have another example, predicate to find the sum of elements in a list. So, how can you write it? You have to use sum list as a function, some function, that means predicate. Sum list, then you have in empty bracket, then 0, that means the initialization, then sum list head tell comma sum, implies that sum list tell sum comma sum is head plus tell sum. So, how you can use it? Sum list, then you have a list 1 2 3 4 comma sum, then it will give you the sum of this all elements of your list. So, you will get the total of 10. So, this will give you the sum. Now, the next program, predicate to reverse a list Prolog. So, reverse list, that means the reverse order of your list. So, reverse list, you have two empty list, then reverse list head and tail part comma reversed, implies that reverse list tail comma reverse tail append reverse tail head reversed. So, how you can use this clause in the example? So, suppose you have reverse list 1 2 3 comma reverse, we will unify rev with reverse. So, we will get the reverse as 3 2 1, this is your reverse list. Predicate to remove the duplicate list from a list. So, how you can remove the duplicate list? So, you have to use remove duplicate empty list and then empty list full stop, remove duplicate head tail and the result, implies that member head comma tail comma remove duplicates tail result, remove duplicate head tail comma head result, implies that member head tail remove duplicate tail result, remove duplicate 1 2 2 3 4 4 5, that means you have 2 2 and 4 4, 2 4 and 2 4, that means the repetition of 2 and repetition of 4 comma unique, will unify unique with 1 2 3 4 5, that will give you the unique list. These examples demonstrate various operations you can perform on list in Prolog, such as summing elements, reversing list and removing duplicates. Prolog's patterns, matching and recursion make it well suited for list manipulation task. In Prolog, you can work with different types of list based on your needs. Here are some common types of list you can use. So, types of list. First, homogeneous list. This list contain element of the same data type. For example, a list of integer or a list of atoms. So, in Prolog, how you can write it? You have a list of 1 2 3 4 5 and apple, banana, cherry. So, this is homogeneous type of list. Next is heterogeneous list. This list can contain element of different data types. They are often used for more complex data structures. So, for example, you have 1 comma hello, it is a string type, then AB comma dog. So, this is the heterogeneous, the which is combination of numbers, string, alphabet and the characters. And next is nested list. A list can contain other list as its element. This allows you to create nested data structure. So, in Prolog, how you can write it? So, in one list you have 1 2 comma 3 4 in another list comma 5 6 in another list. So, this is the nested list. Next is empty list. An empty list is a list with no element. So, how you can define it? With the square bracket with no element. Next is list of variables. List can contain variables, making them placeholder for future values. In Prolog, how you can write it? X, Y, Z all in the capital letters. List of predicates. You can use list to represent predicate or goals in Prolog. So, you have member x, comma 1, 2, 3, comma x is greater than 2, y is x into 2. List of clauses. List can hold a set of Prolog clauses which can be used to define rules and facts. So, you in Prolog, how you can write it? Fact 1, rule 1 and rule 2. Now, come into the application part. Some key application of list in AI. These are some common types of list in Prolog. Lists provide flexibility for representing and manipulating data in various ways, making Prolog suitable for a wide range of applications. Lists are a fundamental data structure in AI and programming in general. They are used in AI for various purposes and applications due to their flexibility and utility. Here are some key applications of list in AI. First, knowledge representation. Lists are often used to represent structured knowledge in AI systems. Facts, rules and data can be organized into lists for easy retrieval and manipulation. Second, search algorithms. In AI search algorithms like depth first search and breadth first search, lists are used to manage and explore nodes or states. Open and closed lists help keep track of visited states during search. Next is planning. AI planner use lists to represent plans or sequence of actions. Planning algorithms generate and manipulate list of actions to achieve goals. Next is natural language processing. Lists are used to represent sentences, words or tokens in text processing. They enable parsing, tokenization and other NLP tasks. Next is machine learning. Lists are used to store data sets which each element in the list represent a data point or example. Features can also be represented as lists. Next is expert systems. Lists are used to represent rules and facts in expert systems. They help encode expert knowledge for decision making. Next application is constraint satisfaction problem. In short, we can call it CSP. Lists can represent domains and variables in CSPs. Constraints can be defined over list of variables. Next application is knowledge graphs. Lists can be used to represent nodes and edges in knowledge graphs. Graphs traversal and querying involves operation on list of connected nodes. Heuristic search. Lists are employed to store and update priority queues in heuristic search algorithms like A* search. Next is pattern matching. Lists are used for pattern matching in AI, such as matching sequence of symbols in symbolic reasoning systems. Next is data processing. In data processing for AI tasks, lists are used for tasks like filtering, feature selection and data transformation. Next application is robotics. Lists can represent sensor data or sequence of actions for robots. Path planning algorithm use lists to generate and follow paths. Next is game development. Lists are used to represent game states, moves and player actions in AI driven game development. Next is agent memory. AI agents including chatbots and virtual assistant use lists to store and manage conversation history, context and user input. In AI, lists are versatile data structure that play a crucial role in representing and manipulating information. They are used in a wide range of AI applications, from knowledge representation to problem solving and data management. Using lists as a data structure offers several advantages in programming and various application domains. Here are some advantages of using lists. First is flexibility. Lists are highly flexible and can store elements of different data types including other lists. This flexibility makes them suitable for representing a wide range of structured data. Next, dynamic sizing. Lists can grow or shrink dynamically, allowing you to add or remove element as needed without specifying a fixed size in advance. This makes them adaptable to changing data requirements. Third, efficient element access. Lists provide efficient access to elements by their positions, that means index. Retrieving or updating elements by index has constant time complexity order of 1 in many programming languages. Next is iteratability. Lists are iteratable, meaning you can easily traverse their elements using loops or iteration. This is valuable for performing operations on each element such as searching, filtering or transforming data. Next, pattern matching. In functional programming languages like Prolog and Haskell, pattern matching on list simplifies program logic and allow conscious and expressive code. Next is data organization. Lists are useful for organizing and structured data. They enable the creation of nested structures such as list of lists, which can represent hierarchical or multidimensional data. Next is memory efficiency. Lists typically use contiguous memory storage, which can lead to efficient memory utilization compared to other data structures like linked list. Next is easy concatenation. Lists can be easily concatenated to combine multiple lists into one. This operation is often efficient and does not require expensive memory copying. Next is common data structures. Lists are standard data structures supported by most programming languages and libraries. This ubiquity makes them a convenient choice for many tasks. Next is functional programming. Lists align well with functional programming paradigm, allowing you to use functions like map, filter and reduce for list transformations, leading to more declarative and readable code. Next is compatibility with algorithms. Many algorithms and data manipulation operations are designed to work with lists, making it easier to leverage exciting libraries and solutions. Next is simplicity. Lists have a straightforward and intuitive syntax for creating and manipulating collections of data, making them accessible to both beginners and experienced programmers. Next is versatility. Lists can be used for wide range of tasks, from simple data storage to complex data processing and algorithm implementation. Next, support for multiple languages. Lists are available in various programming languages including Python, JavaScript, Java, C#, Ruby, Lisp and more, making them a portable concept across different platforms. While lists offer many advantages, it is essential to choose the appropriate data structure based on your specific requirements. Lists may not be the best choice in all situations, and other data structure like arrays, sets or dictionaries may be more suitable for certain tasks. Lists in Prolog, like in many programming languages, have certain limitations. So, here are some limitations of list in Prolog. First, linear access time. Accessing elements in a Prolog list by their index position has linear time complexity order of n, where n is the index of the element. This can be inefficient for large lists. Second, non-mutable. Prolog lists are immutable, meaning you cannot modify individual element in a list once it is created. Instead, you need to create a new list with the desired changes, which can be inefficient for some operations. Third, limited built-in functions. Prolog standards built-in predicates for list manipulation are relatively basic compared to some other programming languages. More complex operation may require custom predicates. Next is nesting complexity. While Prolog supports nested lists, working with deeply nested structure can become complex and harder to read and debug. Memory overhead. Prolog lists may have some memory overhead due to their recursive structure. A list is composed of a head element and a tail, which is another list. Next, limited data types. Prolog lists are typically used for symbolic data, making them less suitable for numeric or binary data. Numeric operation can be less efficient with Prolog list. Next, lack of type checking. Prolog does not perform strong type checking, so it is possible to mix data types in list without warning, potential leading to runtime errors. Next, performance. For certain operations, Prolog list may not be as performant as another data structure such as arrays or specialized data structure due to their recursive nature and pattern matching. Next is pattern matching complexity. While pattern matching is a powerful feature in Prolog, it can lead to complex code when working with nested list and deep structure. Next is limited random access. Prolog lists are not designed for random access to elements. Accessing elements by their index is not an efficient operation. Despite this limitation, Prolog lists remain a versatile and valuable data structure for many symbolic reasoning and knowledge representation tasks in Prolog. In many cases, the limitation can be mitigated through careful design and by leveraging Prolog's another features such as pattern matching and recursion. However, for specific tasks that require efficient random access or mutation of elements, other data structure may be more suitable. Now, after understanding the list, now you can understand the concept of string. In Prolog, strings are typically represented as lists of characters. Each character in the string is an individual element in the list. Prolog does not have a built-in string data type like some other programming languages, so strings are handled as a list of characters. Here is how you can work with a string in Prolog. First, creating a string. To create a string in Prolog, you can simply represent it as a list of characters enclosed in single quotes. So, how you can write in Prolog? Like hello world. So, in a single quote. Next, manipulating strings. You can manipulate strings by using list predicate and operations. For example, to concatenate two strings, Prolog. In Prolog, how you can write it? Append hello, comma, word. So, and the next is result. So, this will unify result with the string hello world. Next, accessing characters. You can access individual characters in a string using list indexing. So, how you can write in Prolog? Prolog, how you can write it? Nth O, comma hello, comma H. Percentage will be unified with H. Nth O 1, comma hello, comma E. %E will be unified with E. Now, string comparison. You can compare string using Prolog predicates like equal sign and double equal sign and compare by 3 and others. In Prolog, how can you write? A, B, C in single inverted comma is then double equal to and the single inverted comma A, B, C. So, percent and percentage true, that means the both string are same. Next is string length. You can find the length of a string using the length by 2. So, how you can write the predicate? Length hello, comma len, len is for the length. %len will be unified with 5 because we have 5 letters in hello. Now, substring. To extract a substring, you can use sub underscore string /5 in a single inverted comma. So, how you can write in Prolog? Substring hello, comma world in the single inverted comma, comma before, comma length after, comma substring. So, it will give you the result of substring with the specified portion of the string. Next is pattern matching. Prolog's pattern matching can be used for more complex string processing such as pattern recognition and extraction. Next, input output. You can read string from input and write string to output in Prolog using standard IO predicates. Keep in mind that while Prolog does not have a dedicated string data type, it provides a robust set of predicates and operations for working with strings represented as list of characters. This approach is well suited for symbolic processing and text based manipulations which are common in Prolog applications like natural language processing and text parsing. In Prolog, strings are typically represented as list of characters. However, it is important to note that Prolog does not have a dedicated built-in string data type. Instead, strings are manipulated as list of character or atoms and they can be categorized into different types based on their characteristics. So, here are some characteristics. First, atom as string. In Prolog, atoms are often used to represent strings. Atoms are sequence of characters enclosed in single quotes. For example, you can write this in the Prolog, hello world. In this case, the single quoted atom represents as a string. List of characters, strings in Prolog are frequently represented as list of characters. Each character is a separate element in the list. For instance, in Prolog, H is in a single quote, E in a single quote, L in a single quote, then L in a single quote, then O in a single quote, then the blank space, then the W is in a single quote, then O, R, L, D all in the single quote. So, how you can write it in a separate comma manner, the single string. This is a common representation for strings in Prolog, and you can perform various list operation on them. So, built-in predicates. Prolog provide built-in predicates like atom characters and the string characters to convert between atoms and list of characters for string manipulation. So, how you can write in the Prolog? Atom chars hello comma list of character. Next is text processing. In many Prolog applications, strings are used for text processing tasks such as parsing, tokenization and pattern matching. Symbolic representation. Prolog often uses string to symbolically represent data, making them suitable for knowledge representation and symbolic reasoning. Input-output strings. Strings are commonly used for input and output operations in Prolog programs, including reading strings from user input or writing string to output streams. While Prolog does not have a dedicated string data type like some other programming languages, it provides a versatile set of features and predicates for working with string represented as list of characters or atoms. The choice of representation depends on the specific requirements of Prolog programs and nature of the text data you are handling. To run a Prolog program that involves string manipulation in the SWI Prolog editors, you can follow these general steps. First, open SWI Prolog, launch the SWI Prolog interpreter or editor on your computer. Second, create or load your Prolog programs. You can either create a new Prolog program by opening a new file or load an existing Prolog source code file using the consult predicate. For example, to load a file named myprolog.pl, you can type the following command in SWI Prolog editor: consult prolog consult myprogram.pl. Next, third step is write your Prolog code. In your Prolog program, define predicates and rules for string manipulation. You can use built-in predicate like atom characters or string characters and other string manipulation predicates to work with strings. Here is an example of a Prolog program that reverse a string. So, in the Prolog program, you have to use reverse string, then string comma reverse implies that atom character string comma characters comma reverse characters comma atom chars in a bracket reverse comma reverse characters. Now, fourth is query your program. After loading your program or defining your predicates, you can use the SWI Prolog interpreter to query your program. You can test your string manipulation predicates with a specific query. For example, to reverse a string, you can enter the following query. In Prolog, you will have a question mark, that means you start with the query. So, question mark, then reverse string hello in a single quote comma reverse. Then the SWI Prolog will respond with the result of the query. So, the result will be the reverse of hello. Next is interact with the SWI Prolog REPL. You can also use the SWI Prolog REPL, that means read, eval, print loop, to interactively test your predicates and experiment with string manipulations. Now save your Prolog program. If you have made changes to your Prolog programs and want to save them for future use, use the save/1 predicate to save the Prolog program to a file. So how you can write it? Save in a bracket myprogram.pl. Next is exit SWI Prolog. When you are finished working with SWI Prolog, you can exit with Prolog program. These are the general steps for running a Prolog program involving string manipulation in the SWI Prolog editors. Remember to replace myprogram.pl with the actual name of your Prolog source code file if you are loading an existing program. So by this you can run the Prolog program. Here PL is the extension for programming logic. So now in the next lecture we will deal with another exciting journey of Prolog programming, and in the next lecture we will discuss about recursion in Prolog programming, where we will discuss many more examples related to recursion. So thank you for watching, and we will see you in the next chapter.